Hello and welcome back to Cartetus Math. So this is the second video for rational expression, so we're actually at video number 12 now. In the last video, we did not cover restrictions, we only covered complex fractions. So I'm actually going to make a little adjustment here to our pacing. So we're going to call section 3.2 restrictions. Ooh, that was already written. We'll take this and away, and then we will change all of this stuff. So now restrictions is kind of his own little section. Okay, so we'll just scroll down, close your eyes so you don't get dizzy. There we go. And we're ready to go on restrictions. So restrictions on rational expression, what is a restriction? What does that even mean? So like in the last video, we spoke a little bit about how fractions are divisions, right? And so when we do divisions, there is a golden rule that we have to follow. And I will give you 5 seconds to take a little brainstorm. What do you think that golden rule is? The one thing you can never do in a division. Let's make it a little bold. When you divide, you can never divide by 0. So that's our golden rule, right? You can never divide by 0. And this is something your teachers have told you forever and ever and ever. You can't divide by 0. And the reason for this is, if we go back up to our description of what division is, the quotative, if we look like our example of 8, right? If we instead had asked 8 divided by 0, then the question would be, how many groups of 0 can we make from 8? We have 8. We can't make any groups of 0. That doesn't make any sense. And then in the partitive example, if we took that and we worded it the same way, 8 divided by 0, it would be how much in each group if we split 8 into 0 groups. Well, again, there is no such thing as 0 groups. That also doesn't make any sense. So that's why we can't divide by 0. And the thing is that when we're dealing with algebra, generally we have the assumption that x can be anything, right? When we have variables, we say, okay, well, this is some number x. We don't know what number, but it's something. And we kind of just work with it that way, assuming that it's a placeholder for some number. But because in this case, when we're dealing with rational expressions, we're dealing with fractions and divisions, because x is in a position of dividing something, x can't be anything. X can be anything except for 0. And so that's what a restriction is a restriction is a statement about what this variable cannot be. So the way that we state restrictions is we say x cannot equal 0, and your reason is because you can't divide by 0. But you don't have to write that part. The only thing that really matters is this, is x cannot equal 0. That is your restriction statement. Okay, so the way that you deal with restrictions is you're always looking at positions of division. So here in the second example, we have x plus 5. And so remember that it's really the divisor as a whole that can't equal 0. So here, my divisor, essentially your first step is locate your divisor. So in this case, your divisor is x plus 5. That's what is doing the dividing, is this whole thing. And your second step is to set up your divisor with cannot equal 0. So this is the setup. We have x plus 5, and x plus 5 cannot equal 0. And the way that you use the cannot equal sign is the exact same way you can use the equal sign. So it just stays here, and it's just making the opposite statement as it would be if you had an equality. So if you wanted x to be equal to 0, in this case, we just want the reverse. We just don't want x to be equal to 0. So here you isolate for x as you would if it was an equal sign. So we minus 5 on both sides, and we get x cannot equal negative 5. Since if x does equal negative 5, then we're going to get 3 over negative 5 plus 5, which is going to give us 3 over 0, which is bad. We don't want that. That's not good. So this is our restriction. X cannot equal negative 5. Okay, so we're going to do the same thing here with the third example. We will have to add a step in this case because we have a slightly more complicated divisor. So our first step is locating our divisor. The thing that is doing the dividing is this down here, 3x squared plus 2x. That's our divisor. Now, because our divisor is a polynomial, second degree, we need to factor it. Step 2 now does not become set up your divisor with does not equal 0. Your step 2 is now fully factor. Fully factor your divisor. So if we have 3x squared plus 2x and we want to fully factor it, what do these two terms have in common? Well, in your coefficients, you have no numbers, no numerical factors in common, but for your variables, you do have an x in common. So you can factor out an x here, you get 3x. When you factor out an x from 2x, you get just 2. So these are your two factors. And so now this is very similar to solving for x with second degree equations, except we're solving for what x cannot be equal to. But the process is exactly the same. So, ooh, I just realized I had a typo here. I wrote step up. That's not what I want to say. Set up. So same thing here. So set up each factor. Set up each factor of your divisor with cannot equal 0. So when we solved second degree equations and we had this situation and we did this, right? We had them equal to 0 and equal to 0. And then we would say, okay, well, this is one factor, x equals 0, and then this is the other factor, and 3x plus 2 equals 0. We are doing the exact same thing in this case, except we have a does not equal 0 statement instead. So we have our first factor, x, and we say x does not equal 0. And we have our second factor, 3x plus 2, and we say that does not equal 0. And we solve for x as we would if this was an equality. So here we minus 2 on both sides. 3x does not equal minus 2. And then we divide by 3 on both sides. So x cannot equal minus 2 over 3. And so this whole situation, these are your restrictions in this case. You have x cannot equal 0 and x cannot equal negative 2 over 3. And that's because if you were to put a 0 in each of these x's, this entire denominator would simplify to 0, which cannot happen because it's a denominator. In the same way, if you put negative 2 over 3 in the space of x here, then the same thing would happen. This entire expression would simplify to 0, which cannot happen because it's a denominator. Okay, so that was that example. I just need to add a little bit more space here because I write too big. Let's squeeze that down there. Okay. So now this one is again a little bit more complicated. And actually, before we jump into this one, I want to point out that notice that when we're stating restrictions and when we're dealing with all of that stuff, the only thing we look at is the denominator. In all of these examples, I haven't even touched the numerator in any of them. I don't care at this point. When you're dealing with just identifying your restrictions and that's the only thing you want to do, you don't actually care what your numerator is. The numerator doesn't bother you because the numerator doesn't do any dividing. The numerator is what gets divided. So it doesn't matter what you have on top. So even in this case where we have 2x plus 1, this can equal 0. I don't care if this equals 0 because it just means I have no things and I put nothing into multiple groups, which right is a weird thing to do, but it's not something that makes no sense. It's not like saying making 0 groups of something. It's just taking nothing and separating nothing. So the numerator doesn't bother us, in short. So we'll just look at the denominator. So same thing here. Step 1 is identify your divisor. That's our divisor right there. Step 2 is to fully factor your divisor. So in this case, we have a trinomial, 6x squared minus 4x minus 2. So since we have a trinomial, we need to use product and sum method. So remember, this is our A, this is our B, this is our C. Product and sum, you need to start with A times C. That's going to give you 6 times negative 2, which is negative 12. So we have to make it rain factors, put our little factor umbrella. And this is actually something I saw in a different instructional video that I really liked. So I'm going to show you a different way. When you have a negative A times C, a nice way to list all your factors is, so normally we would do 1 and 12 and then move on to 2. I'm not going to do that here. I'm going to do 1 and 12 and then 1 and 12 again. One case where 1 is negative and 12 is positive, and the other case where 1 is positive and 12 is negative. And so do that for all your factors. So you have negative 2, positive 6, positive 2, negative 6. Since this is actually your full list of factors of things that multiply to give you a negative 12. Before we were kind of just trying to do the mental gymnastics, and it's really difficult to do that. So I wish I could credit the person who explained it this way, but I don't remember where I saw it. So this is our list of all of our factors, positive and negative factors, that will multiply to a negative 12. And now we can just look at what we get when we add them up. So here we get 11, negative 11, 4, negative 4, 1, negative 1. And the one that we're looking for is negative 4. So that's this one, which means these are the factors we need. So we have 6x squared. Negative 4 is going to get broken up into plus 2x and minus 6x. And we're going to group this guy. So here we can factor out a 2x. We'll get 3x plus 1. And here we can factor out a negative 2. And again, we're going to get 3x plus 1. So this whole thing can be rewritten as 2x minus 2 and 3x plus 1. So that is now our fully factored trinomial, which is our divisor. And now we want to do our third step, which is set this up so that it does not equal 0. So this entire expression, if we were solving a second degree equation, this entire way, it would have said equals 0, equals 0, equals 0, equals 0. We're just going to do the same thing, but with a does not equal 0. So this is the statement we're left with. This does not equal 0. And so we have to do factor by factor. This does not equal 0, and this does not equal 0. Because remember, these two things are being multiplied. So if this piece is 0, that's going to make the entire expression simplified to a 0. If this piece here is 0, then again, the entire thing will simplify to a 0. So we have 2x minus 2 cannot equal 0. Let's show all the work. Add 2 to both sides, we get 2x cannot equal 2. Divide by 2 on both sides, we get x cannot equal 1. And then for the second factor, 3x plus 1 cannot equal 0. We have to subtract 1 on each side. 3x does not equal negative 1. And then we have to divide by 3 on each side. So x cannot equal a negative 1/3. And these are our restrictions. And again, just to say it one more time, the numerator doesn't bother us. We don't care. The only thing we care about with restrictions is the denominator and what number will make that denominator 0. In this case, x equaling 1 and x equaling negative 1/3, that will make this entire denominator 0, which cannot happen. Okay, so now we have this fifth example, and this is a complicated one. So this is a fraction all over another fraction. So we can rewrite this as x squared over 3 divided by y over 3x. So these are complicated because if you just take a quick look here, and I told you do step 1, identify your divisor, a lot of you would say, okay, well here 3 is a divisor because it's in the denominator, and 3x is a divisor because it's in the denominator. But there is another divisor here, and that would be y. Y is a divisor because this front term is being divided by the entire second term, which means we have 3 things that are divisors here. And the easiest way to see it is when you have it written like this, everything underneath that first line is a divisor at some point in the process. So none of these can be 0. The 3 doesn't bother us because there's no variable there, but if there was, it would also be a divisor. So here we need to put restrictions on each of these. The 3 doesn't matter, it's no big deal. And luckily for us, these are very simple. So we can just say y cannot equal 0, since if it did, we would be dividing by some type of 0. We would be dividing by a 0 here. And 3x cannot equal 0. And here we have to isolate for x. Divide by 3 on both sides. 0 divided by 3 is still 0. We're taking nothing, we're putting it into 3 groups. We still got nothing. So x cannot be equal to 0. And these are our 2 restrictions for this example. So the restrictions themselves are quite simple. What's difficult here is this formatting of fraction on fraction on fraction. Okay, and now there's just a few examples in here that I would like to show you. The ones that have to do with the adding. Okay, what's a difficult one? So this one, these two look complicated, but these are just regular fractions down here. So you really can just punch these into your calculator. I don't want to worry too much about these. let's do this one here, number 16, because we've got two A's. So here in the numerator, so the first thing we're going to do is we're going to rewrite this whole thing. So we'll rewrite the whole thing. So we're going to take this entire front piece, and we'll write a over 5 minus 2 over a squared. That whole thing is in brackets, and that is being divided by 2 over 25. So I kind of wrote it in a way so that it's less vertical, and we can work with it chunk by chunk. So we're going to deal within the brackets first, and bad math is still something that matters. And since we're doing a subtraction, we need a common denominator here. And right now we don't have one. We're going to need one, which means that over here we need to multiply top and bottom by an a squared. So let's make a little bit of space, just a little, shrink this down a little. Okay, so a squared over a squared. So just to make sure everything is crystal clear here, a squared over a squared, that would simplify to 1, right? The same way that 2 over 2 is 1, or pi over pi is 1, or 86 over 86 is also 1. Any case where your numerator and denominator are the exact same number, it's 1. So this is just saying a over 5 times 1. I'm not changing anything. This entire expression, it's preserved. It's not being changed. I'm just creating a common factor on the bottom, or a common denominator on the bottom. So now I have a denominator of a squared times 5, and I want the same thing on this side. I also want an a squared times 5. So to get that, the bottom's going to need to be multiplied by 5. But in order for me to not change this entire thing, I can't just multiply by 5 on the bottom. I have to also multiply by 5 on the top so that I don't change anything. So here, now we can simplify all of this. So a squared times a, that's going to give us a to the power of 3. Down here we have a squared times 5, which we can express as 5a squared, minus 2 over also 5a squared, and this is divided by 2 over 25. Okay, so now over here, this whole thing, these are common denominators, which means that we can combine this top piece. And we can put all of this on one denominator, right? So you can think of this a little number example, and I find number examples help me remember, or just to clarify what's happening. So if we had 3 over 4 minus 1 over 4, we can rewrite this as 3 minus 1 over 4, which is the same as 2 over 4. Right? So both of these things mean the exact same thing. In this case, it's just that we don't know what this number is. We don't have a number for a cubed, we just have a cubed. So we leave it there as a full expression. Let's get that out of the way. Okay, so that mostly deals with the first term, and now over here we have this division of a fraction. Remember how we deal with division of a fraction? This division turns into a multiplication, and then the fraction flips to compensate for that change. So here we have 25 over 2. And here we can multiply straight across. But I actually want to do something a little bit different. What I'm going to do here is I'm going to switch the spots of the 25 and all of this. I'm going to write 25 times a cubed minus 2. And over here we have 5a squared times 2. Okay, and I'm writing it this for a specific reason, which you'll see in a second. So 25, you can do this division here, basically, is what I'm trying to show. You can do 25 divided by 25. And if you're not sure, I'm sure you know 25 divided by 25 is 5. But then if you're not really sure, because of all the fraction business, where that 5 goes, this is what I want to show, is that 25 can be rewritten as 5 times 5. So you can really visualize those 5s. And it's not canceling in the sense of they disappear, is that we cross them out because 5 over 5 is just 1. And it's redundant to leave a times 1 there. So that's why we can cross those out. And then we have this mostly simplified expression. Now that we've taken that 5 out, we can multiply this in, and we will have 5a cubed minus 10 over 2a squared. And that is our simplified expression. So that was just to show how to kind of manipulate these and simplify them. Also, we should have also dealt with the restrictions at some point. The only restriction we have here, so for restrictions, if we go way back to the beginning, we just need to identify a divisor. So here we have a variable, it's in the numerator, so it's fine. And then we have another variable here, a squared, which is in the denominator. So this is a divisor, and this is actually our only restriction. So a squared cannot equal 0. And you can absolutely do a square root on each side. There's no problem there. And you just get a cannot equal 0. And that is your only restriction here. So this example is really to demonstrate kind of how you flip things around, do your common denominators, and all of that stuff. Okay, so I think I'm going to end this one off here so that it doesn't drag on as long as the last one. Thanks for stopping by as usual, and in the next video we will look at simplifying. Where did all my notes go? Sorry, I'm scrolling back up. Yeah. So in the next one we will be dealing with, there's supposed to be a section here for simplifying, so I think we're actually going to have to adjust that as well. And add in a 3.2.1, which talks about simplifying rational expressions. So I will add that in for you guys so that you can see, so you can have some more intense examples with just simplifying rational expressions. There is quite a bit of simplifying that's built into multiplying, but we'll get there when we get there. Okay, so that's the end of video number 12. I will see you in the next one.